Right. So what we were doing last time, we were working our way through theorem 3.15, looking at properties of these sequence spaces that we've defined. So we've got little c0, we've got little lp, and little l infinity, and c double zero. And what have we proved so far? Well, we proved that little l infinity was complete with a Banach space. So we've shown that L infinity with a Banach space, and we showed that C0 is a closed subspace of L infinity. So that makes C0 a Banach space as well when you use the norm infinity on it. So we proved that this is the Banach space, and we've done L infinity. We haven't done the other LPs. What I'm going to do for you is little L1, and the other LPs are pretty much the same. So we'll do little L1 in a minute. And then the other thing we haven't done, let's see, we have seen that C00 is not dense in L infinity, but we haven't yet seen that it is dense in LP. And again, I'll prove that for you for little L1, but the proof is the same for the other P's. So then we had all those proofs. But so we're going to be focusing on probably the little L1 to finish this section, the completeness of little L1, and the fact that C00 is dense. So here's all the proofs that we've been doing before with that notation for sequences of sequences. I'll remind you, because we'll be doing that again in a minute. So we had things like this coming up, a sequence of sequences where the nth term of the kth sequence was x with an upper bracketed k and a lower n. And that was how we dealt with little l infinity, and we'll do the same with little L1. In past years, I've sometimes done x upper bracket n for the nth sequence and had the kth term. It really doesn't matter. If you swap n and k around correctly and consistently, that's not a problem at all, or indeed use any other indices, as long as you make it clear what you're doing. There was at least one typo. There was a stage in the middle of the L infinity proof where I swapped my k's and n's around and had them in the wrong places, and I fixed them all except this was stage 2 of the proof that little L infinity was complete. By the time I tried to fix everything, I had lost one little k, which should have been there, fixed in the annotated slides, but there you are. It should be k greater or equal to n there. And when I did the proof that C0 was closed in L infinity using sequences, I used an epsilon over 3 proof where I could have got away with an epsilon over 2 proof, but it doesn't make any difference. Okay, so to finish the section then, so to finish section 3.4, we'll show that L1 with norm 1 is complete, and that C00 is dense in L1 norm 1, and for P between 1 and infinity exclusive, the proof is similar. So let's have the completeness of little L1 with norm 1. This is going to be a very familiar proof structure by now. So let's let xk, where k goes from 1 to infinity, be a Cauchy sequence in L1 with norm 1. So we have our usual notation. So as usual, we have the case sequence is given by xkn, n equals 1 to infinity. That's in f to the natural numbers. Well, it's in L1. So your nth term of the case sequence is our usual notation. And as usual, we have a two-stage proof. So what do you think stage 1 is going to be? Point-wise convergence, or term-wise convergence, or coordinate-wise convergence, whatever you want to call it. We show that xk converges term-wise. Try and find a difficult word to write. Term-wise. Anyway, or you could say coordinate-wise. Or you could say point-wise, as you say. They all pretty much mean the same thing here. Well, it's the usual thing. So let k and m be natural numbers. Then yet again, as usual, just the modulus of xkn minus, for each natural number n, xnk minus xkn minus xmn. That's one of the terms to be added in the L1 norm of the difference of the sequences. So it's actually less than or equal to the norm of xk minus xm1, just as usual. Remembering that this one norm is just the sum of all of the moduli of the differences, and this is just one of them, so obviously any one term is less than or equal to the sum of them. Same works in all the other LPs as well. So since xk is norm 1 Cauchy, it follows that this sequence of nth coordinates is Cauchy as well. This is from k equals 1 to infinity. That's Cauchy in your field. And so this sequence converges. So, as usual, we'll set xn to be the limit of that sequence. and this is for every natural number n. So for every natural number n, you get a different sequence, probably. As k varies, you let k tend to infinity to find out what xn is. And now you've got termwise convergence. That's in f to the n, and let's call that x. And then xk converges to x termwise as k tends to infinity. So what do you think stage 2 is going to be?
Uniform convergence.
You think uniform convergence? Any other suggestions? Which space are we in at the moment?
Oh, we have now proved the pointwise convergence.
Yes.
So by using that one, we can always do uniform convergence.
I'm not sure about the uniform convergence because we're dealing with a different space this time. Last time we were trying to deal with L infinity, which is where you have uniform convergence. It may be that by uniform convergence you mean something else. Uniform convergence.
Stronger convergence anyway.
We must prove the correct kind of convergence in order to get this to work. So proving uniform convergence would not be enough for this particular problem, because uniform convergence does not imply L1 convergence. So we have to be a bit careful.
Normalized anyway.
Yes, that's right. We want norm convergence. So we want norm 1 convergence in this particular case. Okay? And yes, uniform convergence will also be true. And so you're right that we will have succeeded in proving uniform convergence, but it wouldn't quite be enough to prove uniform convergence. Okay, so stage 2. Remember, at the moment, x is just it's just some sequence of scalars. We don't know anything about where it is. We have to show that x is in L1 and that norm xk minus x1 tends to 0 as k tends to infinity. And as usual, we do both of those together. So we let epsilon greater than 0. And this is even maybe slightly more subtle than the little L infinity version, where it's similar anyway. You'll see how this works. So we start by, since xk is Cauchy, there is a natural number n such that for all little k and little m greater or equal to capital N, we have the L1 norm of the difference less than or equal to epsilon, or less than, it doesn't matter. So what we claim is that for all k greater or equal to n, we have xk minus x is in L1 and the 1 norm of xk minus x is less than or equal to epsilon. The result quickly follows from this. And here I'm putting this statement star for what we do know. And of course, we want to let little m tend to infinity, but as usual, we have to do it carefully. It would be nice to just say, we know that xk minus xm1 is less equal to epsilon, and that xm tends to x termwise, and therefore we can just take the limit, but then a termwise limit isn't necessarily the same as a norm 1 limit unless you have extra information. So you actually have to be a little bit careful here, and it's quite a subtle proof, because in general, a termwise limit is not the same as a norm 1 limit. But we're using the additional power of the cosinus, as usual, to get us home. So, okay, so let me call this one dagger. So we're going to use star to prove dagger, but we have to do it carefully. So we start by fix k greater or equal to n and little m greater or equal to n. This is temporarily, and a capital M in the natural numbers temporarily. Then what do we have? Star tells us something about xk minus xm. And what I'm going to look at is a finite sum, because finite sums are much better when it comes to termwise. So you've got the sum from just move that up a bit. The sum from k, no, I can't use k, let's have another one. The sum from j equals 1 up to capital M of the modulus of xkj minus xmj. That's a bit of the one norm sum. So that's less than or equal to the sum from j equals 1 to infinity of the modulus of the difference. Which is the one norm of the difference. And that's the one norm of the difference between xk and xm. Which is less equal to epsilon. That's the bit where we use star. The rest of it is just the definition of the one norm. Now, keeping k and capital M fixed, we let little m tend to infinity. We're allowed to do that. K and m as above fixed. You can let m tend to infinity. Well, you daren't do it in in a limit of infinite sums because you can't interchange limit and infinite sums in general. But you can interchange limit and finite sums. So what happens to this first sum as little m tends to infinity? It's a finite sum of terms, and the terms tend to, well, you just look at what the terms are tending to, and you can substitute in xj instead of xmj. So sum from j equals 1 to capital M of the modulus of xkj minus xj is less than or equal to epsilon. Notice this is true for all k and capital M as above. And we did that by using the term-wise limit. Now this is true for all little k and all capital M in the natural number, sorry, all little k greater or equal to capital M, and for all positive integers capital M. So now we're allowed to let capital M tend to infinity. To obtain sum from j equals 1 to infinity of mod xk j minus xj. Again, this is, we're keeping k fixed in this. So k is still fixed. You don't have to keep saying that. And that is still less than or equal to epsilon, because it's the limit of the finite terms, limit of the finite partial sums. They're all less than or equal to epsilon, so the final one is. In other words, xk minus x, oops, we don't need that, xk minus x is in L1. And norm xk minus x1 is less than or equal to epsilon. And since that was true for all little k greater than capital N, that proves dagger. And the result follows. And as I said, the result follows quickly from this. Let's just remind you how that works. Then x is equal to xk minus x is in L1. And, well, I should have said that before, in fact. Okay, that's right. No, that's okay, we've done that right. And the result follows. So, tricky proof there because we had to do a lot of temporary fixing things and let things converge to infinity in the right order. Do any of those in the wrong order and you get an invalid argument, because pointwise convergence doesn't imply L1 convergence, and so on. We're, again, operating at the limits of what you can actually prove to be true. It's the pointwise convergence. Well, you started with a Cauchy, then you bootstrap with that, prove you get Cauchy and pointwise convergence, and then the combination of Cauchy and pointwise convergence is very powerful, but with care, you get the final result. Okay. So, as I say, little LP proof is very similar. Almost identical. And then for C00 being dense in L1, let's see how that works. with the 1 norm, of course. And again, little LP is similar as long as P isn't infinity. Remember, this one is actually false when P is infinity. We know that C00 is not dense in little L infinity because that follows from some of our earlier comments. I'm going to prove sequential denseness. Sequential denseness, that's that every point in little L1 is a limit of a sequence of points from C00. I cannot write the word denseness at the moment. Let's try again. Denseness. That's what I want. So every point in little L1 is a limit of a sequence of points of C00. But of course, these points are themselves sequences. So let's have a look at this. Let x equals xn, n equals 1 to infinity, be an element of little L1. Then, of course, the sum from j equals 1 to infinity of the modulus of xj is smaller than infinity. That's what the L1 norm is. What can you tell me about the tail of a series? Suppose you sum, instead of summing from 1 to infinity, you sum from, say, little m to infinity or something like that. What happens? Let's write that down. Consider the tail of the series. Sum from j equals m to infinity of modulus xj, where m is some natural number. What happens to that? This is just a fact about series of real numbers. So what can you tell me about that? Yeah? Still finite, that's right. And no bigger than it was before, but you can say a bit more than that. What happens as you let m tend to infinity? That's right. The tail of a series must tend to 0 as you let m tend to infinity. So that's a standard fact that you can revise about real series. Nothing fancy at all. So the limit as m tends to infinity of the sum from j equals m to infinity of modulus of xj is 0. That's because the series had a finite sum, of course. This is, of course, completely false. If the series has an infinite sum, then, in fact, all of these will be infinite as well. So it's a dichotomy. Either, when you're summing positive terms like this, you're either going to get the the limit is infinity or the limit is 0 when you do it like this. So, what do you think I should do to try to approximate my little element of little L1 using a C00 sequence? A C00 sequence is one. I'm not allowed to use the sequence xn itself. A C00 sequence, I have to stop at some point and let all my terms be 0. So what should I do?
You can find a proper subsequence which you can approximate.
Okay. So if I take a subsequence of xn, there is a danger that there'll be infinitely many non-zero terms. And I'm not allowed to do that if I want to be in C00. So I have to be, again, a little bit careful. I want to approximate using something in C00 instead. So I can't just use a subsequence of the xn's. Any?
Cauchy ones or any other inner line, not in Cauchy.
No, it's slightly easier than that in this case. Any? Yes? Partial sums. Well, I'm not quite. I think you've got the right idea, but I'm not sure you're using the correct terminology. I need to choose. I want to choose a sequence that's quite close somehow to the sequence to this term xn, but I'm not allowed to. I have to specify some stage where all the terms are going to be 0 from then on. So let me consider xm in C00 defined by, and we're using the same xn's as above, right? This is in terms of x. I want something that's going to be quite close to x. What shall we do? So we've got our original sequence, which is just x1, x2, x3, x4, a sequence of scalars, remember? Now I want to make a new sequence that's going to be quite close to it, using some of the things we've been looking at. But we have to use a C00 sequence. And you said partial sums, and I think you probably mean what I'm intending, which is the idea is to sort of truncate your sequence. xm is the following sequence. So it's x1, x2, up to x. I'll go up to xm, but then do 0 from there and onwards. So xmj is xj with the xj as above if j is small or equal to m, and naught if j is greater than m. So notice that each of these is a sequence, and each of them is in C00. Of course, it's also in L1. But C00 is a subset of all of these sequence spaces. So now you want to see how close is this to X. Let's have a look at the difference in the sequences. Let's do X minus XM, just for a change. It's the following sequence. It's 0, 0, 0. There are m of these. And then it goes xm plus 1, xm plus 2, and so on. So if you want to see how close did xm get to x, well, xm eliminates the first m terms and leaves you the remainder. So now let's estimate the one norm of that. That's exactly equal to the sum from j equals m plus 1 to infinity of the modulus of xm, of xj, which is, again, a tail of the series, and it tends to 0 as m tends to infinity. and so C00 is density middle of 1. Okay, any final questions on any of these proofs we've been doing in section 3.4? If not, we'll stop there and I'll start up. We'll have a brief introduction to section 3.5.